This talk was given at the 12th International Workshop on Ring Imaging Cherenkov detectors in the city of Mainz, Germany on Tuesday, 16th September 2025. Thank you for having me. My talk is about overcoming the limits of imaging atmospheric Cherenkov telescopes with the novel cherenkov-plenoscope. Since we have discovered Cherenkov radiation from air showers, we tried to use it for astronomy. Notably, Hillers, Weeks and friends started to think about imaging. And imaging turned out to be a good idea. In fact, imaging worked so well that we all came together to rush towards a major atmospheric Cherenkov detector for astroparticle physics. From here on, we pushed on three key aspects in particular to lower the energy threshold and to improve the reconstruction power for cosmic gamma rays. These are finer pixelation and moving up onto mountains, larger mirrors and moving up into the highlands, larger mirrors, and finer pixelation, larger mirrors and finer pixelation. Imaging with Cherenkov telescopes has come a long way. But now that we have entered the latest and truly amazing generation of telescopes, the physical limits of imaging with telescopes start to show. The square cube law makes it increasingly difficult to build ever larger telescopes because the volume, and thus the mass, and thus the gravitational forces scale cubic, whereas the areas which have to tolerate these forces only scale quadratic. While the square cube law can at least be postponed by spending more resources and engineering, the physical limit of a narrowing depth of field cannot be postponed. It turns out that the three key measures we pushed on to lower the energy threshold and to improve the reconstruction power for cosmic gamma rays, these were enlarging the mirrors, moving up onto mountains, and densening the pixelation, all narrow the telescope's depth of field and thus blur its images irrecoverably. For example, and for reasons which will become obvious in a few moments, an instrument with a 71-meter mirror, a focal ratio of 1.5, a fine pixelation, and its focus set to 10 kilometers will only be able to make a sharp image within a 1.6 kilometer narrow range. And this is a problem, because the air showers which we want to observe exceed this sharp range by about an order of magnitude. It turns out that the telescope's suffering from aberrations, the cause of its narrow depth of field, and the telescope's suffering from deformations and misalignments are all related to the telescope with its mirror and its camera full of photosensors not knowing where a photon was reflected on its mirror. After all the photons with trajectories in this beam of light will be absorbed by the same photosensor. Now imagine there was a new class of instrument which had a mirror just like the telescope, but a camera capable of measuring finer beams of light. After all, the observables we are after to reconstruct the air shower are the Cherenkov photon's direction and impact position. Now even when the mirror of the novel instrument was deformed, or its camera was misaligned, the fine beams would still allow to constrain the trajectory of the photon with respect to the atmosphere. At this point, we can mentally leave all the optics behind and concentrate on the bundle of measured trajectories instead. Now we can trace these photons through a model of a perfect imaging optics such as the thin lens. Here we can compute images free of aberrations and with the focus set to any depth we want. To build such an instrument, we upgrade each photosensor of the telescope with an eye made out of a lens and an opposing array of photosensors. The resulting cherenkov-plenoscope has much finer beams of light and can constrain the trajectories of photons much better than a telescope can do. To discuss the optical performance, we now take a look at a specific design for a Cherenkov-plenoscope named Portal. Portal's goal is to lower the energy threshold of the atmospheric Cherenkov method down to 1 giga electronvolt for cosmic gamma rays. So together with our colleagues from civil engineering, we gave Portal 2 independent cable robots to mount and point its camera and mirror separately. Portal's mirror is 71 meters in diameter and has a focal ratio of 1.5. When pointing, the cable robots move in opposite directions to effectively rotate both mirror and camera around their common center. Unlike the altitude azimuth mount, the cable robot has no singularity near the zenith, what allows it to always move along the great circle and thus makes it intrinsically faster. Portal's eyes are made out of a spherical lens and an array of 61 photosensors behind it, here shown in red. To compare the plenoscope to a telescope and to get a feeling for the scaling of plenoptic perception, we introduce two more instruments, which are identical to Portal except for where Portal has 61 photosensors in each eye, the plenoscope named P7 has only 7 photosensors in its eye, and the telescope named P1 only has 1 photosensor in each eye. Further, we will also benchmark the optical performance when the optics is deformed and misaligned. So we deform the mirror on purpose in a way that will turn out to be significant. And we will also misalign the camera on purpose, again in a way that will turn out to be significant. Now let's have a look at the point spread functions. We start with the telescope, P1, when the mirror is in a good shape and the camera is well aligned. As expected, the center of the image is sharp, but aberrations quickly blur the image when we go off the optical axis. Already, the plenoscope P7 is able to reduce the aberrations significantly. With the Portal plenoscope P61, aberrations are practically gone. This is again the telescope P1. We see the solid angle of the point spread function versus the angle of the optical axis. By contrast, here's the plenoscope P7 and the Portal plenoscope P61, and here are all of them together. Note, this is a logarithmic scale. But what if the mirror is being deformed? Oof, as expected, the telescope P1 does not like this. The point spread function is all over the place. By contrast, this is the plenoscope P7. Already a significant improvement. And this is the Portal plenoscope P61. And it looks like we are back in gamma ray observation business. We could actually do gamma ray astronomy with this plenoscope despite the mirror being deformed. Telescope P1, plenoscope P7, and Portal plenoscope P61, and here all of them together. There are really worlds between these instruments. Now what if the camera is being misaligned? Again, the telescope P1 does not like this at all. By contrast, the plenoscope P7 and especially the Portal plenoscope P61 brings us back into gamma ray observation business. Again, we can observe gamma rays with this instrument despite the camera being misaligned. Telescope P1, plenoscope P7 and the Portal plenoscope P61, and here all of them together. At this point, I think it's fair to say the plenoscope is in a class of its own. Another unique feature of the plenoscope is its ability to refocus images in post after the recording. To demonstrate this, we set up a phantom source. The phantom source was chosen so that everyone can formulate a clear expectation of what the refocused images should look like. So we take the recordings and project them onto images using the sin-lens equation. Here we start with an image with its focus set to about 2 kilometers. Here at about 2 to 3 kilometers we find the sharpest images of the triangle symbol. Remember the triangle symbol, it's gonna be important later on. Now we can extend the focus and move slowly further up to about 4 to 5 kilometers. Here we find the sharpest image of the spiral symbol. And note how flat the image is. The spiral looks sharp over the entire field of view. When we move the focus further up, we find the sharpest image of the sun symbol, here at about 6 to 7 kilometers. And again, look how flat the image is. One can hardly see any aberrations. Further up, at about 11 to 12 kilometers, we find the sharpest image of the capital letter A. And look how straight these lines are. there is hardly any sign of distortion to be seen. When we move the focus even further up, to about 20 kilometers, we find the sharpest image of the cross symbol. But wait a moment. I told you the triangle structure would be important later on. But where is the triangle structure now? The triangle is blurred beyond recognition. If this image was recorded by a telescope, you would not have known that there was a triangle. This is what the physical limit of a narrow depth of field is all about. After we have observed the phantom source, we will now have a look at the recordings of air showers. This is the simulated recording of a 900 giga electronvolt helium nuclei and its air shower. We will zoom into the black square. The plenoscope turns the two-dimensional islands from telescope images into three-dimensional jets. Note how the individual structures move along the image when we move up and down the focus. Here we see a proton air shower with 44 gigaelectronvolts. The plenoscope no longer misidentifies parts of Cherenkov rings to be high-altitude air showers, as it can refocus to reveal nearby muons. So again, we're gonna zoom into the black box and now adjust the focus down from 25 kilometers, 15 kilometers, until we clearly see that this light was probably emitted by a nearby source only 5 to 4 kilometers in front of the instrument. Here we see a gamma-ray air shower with an energy of 529 gigaelectronvolt. I will not comment on this one. Instead, I want to invite you to wonder with me what Trevor Weeks and Michael Hillers would have commented on this. And finally, we see a low-energy gamma-ray shower with only 3.2 gigaelectronvolt. And here the race to extract better features has just begun. Now obviously, Werner Hofmann and I investigate the cherenkov-plenoscope because we hope that it has implications for astronomy, for gamma-ray astronomy, and potentially also for gravitational wave astronomy. We already do have some preliminary results, don't hesitate to ask us, but as the ring imaging Cherenkov workshop is more focused on hardware, we will now talk a little bit about the story behind plenoptic perception so that you can catch some references to maybe build your own plenoptic instrument. The history of plenoptics, light fields, wavefronts, integral images and lenticular optics are all related to plenoptic perception. In 1904, Hartmann started to investigate aberrations systematically by using masks of imaging lenses. With these masks, he was blocking the apertures of lenses to investigate the circle of confusion. In 1908, Lippmann suggested to use an array of lenses to build a display which would allow the perception of depth. Lippmann proposed to use an array of lenses for this. And in the 1940s, Lippmann's lens array became a reality. And dedicated cameras were made to create the required integral images. Since then, children all over the world are mesmerized by these lenticular displays, and I am sure that you have also seen one before. In a more serious environment, Scheck was asked to develop a camera to track satellites from ground, but atmospheric distortions limited all progress. Scheck realized that with Hartmann's filter, one could monitor distortions caused by the atmosphere. And Scheck's student, Pat, came up with a particular practical solution, an array of lenses. One of Platt's lens arrays made its way to the European Southern Observatory, where Wilson realized the potential to characterize telescope optics. And these efforts eventually led to today's atmospheric correction systems with guide stars. In 2002, Bergholm designs a handheld optics which allows a single eye to perceive depth. Beginning in 2005, a group of computer vision and graphics experts at Stanford built the first handheld plenoptic camera. And NG realized the potential to refocus images. Lavoie proposes to build a light field microscope to overcome the depth of field limits in microscopy. And Hanrahan realizes the potential to resolve aberrations. Based on what they found, NG and friends found the company Lytro. In 2011, Toshiba realizes Lippmann's display for motion pictures for everyone to buy. In about 2015, I think, the professional photographer Wernerson documented how he built a light field camera from scratch. And finally, if I may say so, we contributed a concise compute formalism which includes aberrations, distortions, misalignments, and deformations all in one step. And this is, I think, a novelty. And as far as I can tell, we were the first to discuss the compensation of aberrations in the time domain, a rare problem, but very much appreciated by people hunting nanoseconds flashes of Cherenkov light. In conclusion, the cherenkov-plenoscope has the potential to push the atmospheric Cherenkov method beyond the physical limits of the telescope. The concept of modeling beams of light and computing images after the fact has great potential to widen the field of view, to compensate deformations in the mirror, to compensate misalignments of the camera, and to effectively overcome astronomy's arch-nemesis, aberrations. The compensation of deformations and misalignments works around the limits of the square-cube law and allows us to build larger mirrors more cost-effectively. The refocusing of air shower images after the fact turns the physical limit of a narrowing depth of field into the perception of this depth. As the cherenkov-plenoscope can have all these advantages at the same time, the next generation of astronomers might have the opportunity to build a gamma-ray timing explorer. For the first time, we might be able to collect the abundant cosmic gamma rays in the 1 giga electronvolt domain, for which the universe is still transparent up to high redshifts, in huge collecting areas with the size of soccer fields. Gathering a large counting statistics of cosmic gamma rays in a short amount of time is probably the key to better understand gamma ray bursts, the acceleration of cosmic rays in reoccurring novae, and to implement a gamma-ray-based pulsar timing array to observe the early, low-frequency gravitational waves released just after the Big Bang. Alright, I hope you enjoyed your daily science snippet. Now go and get yourself some lenses to experiment with your own Plenoptic instrument. My name is Sebastian Achim Müller, and this work would not exist without the early backing provided by Adrian Bieland and Felicitas Paus from the ETH Zurich, and the current backing provided by Werner Hofmann and Jim Hinton from the Max Planck Institute for Nuclear Physics in Heidelberg. You can find more information about the Cherenkov-plenoscope on github.com/cherenkov-plenoscope.